Okay, let's dive right into this. Welcome to today's Explainer, where we're going to explore the absolutely fascinating, kind of invisible science of how materials stretch, bend, and ultimately break. You know, we rely on physical materials every single second of our lives, from the floors we're standing on right now to the vehicles we drive, but we rarely stop to think about the incredible forces acting on them all the time. So today, we're taking a stress test journey into the mechanical properties of our world.
It really all starts with a simple, everyday question. Have you ever wondered why a glass window will shatter into a million pieces the second it takes a hard impact, but a massive steel beam can bend and flex under immense weight without snapping? Well, the answers don't just lie in the materials themselves, but in the hidden physical rules and mechanical properties that govern basically every object we interact with.
Section 1. Types of mechanical forces. The invisible pressures all around us.
When a material is just sitting there, resting, it's totally fine. But what happens when we apply external stress? Think about a classic game of tug of war. That pulling action creates what we call tensile force. Now consider a massive suspension bridge. It's actually experiencing two totally different forces at the exact same time. The giant cables holding up the bridge are being pulled extremely taut. That's tensile force, just like the tug of war. But the huge concrete pillars supporting those cables, they're being driven down into the earth by the weight of the bridge. That pushing action creates our second major force, which is compressive force.
To make this super concrete, just imagine holding a standard wooden ruler. If you push inward on both ends of it, you are applying compressive force. Depending on how hard you push, the material is eventually going to react, and, well, as anyone who accidentally snapped a ruler in middle school math class knows, that reaction can be pretty dramatic.
But pushing and pulling aren't the only ways to stress a material out. Think about a pair of scissors cleanly slicing through a ribbon. This brilliantly illustrates shear force. It happens when unaligned forces push one part of an object in one specific direction and another part in the exact opposite direction. Or think about wringing out a wet towel. That twisting action, that's what we call torsational force.
So, whenever any of these external stresses, whether it's tensile, compressive, shear, or torsional, are applied, materials have to react. They deform. And in the world of engineering and materials science, we measure that deformation as strain. Strain is essentially just the elongation or contraction of a material, expressed as a ratio of its change in length compared to its original length. Simply put, stress is the action and strain is the reaction.
Section 2. The science of bouncing back. Elasticity and Young's modulus.
What exactly happens at the microscopic level when you stretch a material? Well, when a relatively small load is applied, the actual atomic bonds inside the material stretch just a tiny bit away from their normal equilibrium. They're pulling apart, sure, but they haven't broken. And the cool part is, when you remove that load, when you just let go, the attractive force between the atoms pulls them right back to their initial starting positions. It's completely temporary.
But obviously, not all materials stretch the same way. A rubber band behaves differently than a steel cable. This is where Young's modulus comes in. You can basically think of it as a material's stiffness score. Represented by the letter E in Hooke's law, it measures how well a material resists elastic deformation. The greater the modulus, the stiffer the material. To put that into perspective, a relatively soft metal like magnesium has a Young's modulus of about 45 gigapascals. But a highly resistant super stiff metal like tungsten, that sits way up at 407 gigapascals.
Now, what's really interesting about stretching an object is the physical reality of its shape change. When you pull on a piece of metal, it doesn't just get longer. As it elongates in the direction you're pulling it, it simultaneously constricts on the sides. Think about stretching a piece of taffy or dough. As you pull it, it inherently gets noticeably thinner in the middle, right?
Engineers absolutely have to account for this thinning effect, and they measure it using something called Poisson's ratio. It's the exact ratio between that lateral thinning and axial stretching. And why does this matter in the real world? Well, imagine you're out off-roading, you get your 5,000-kilogram truck bogged down in deep mud, and you need to use a winch to pull it out. That winch relies on a 10-millimeter steel cable. An engineer had to use steel's specific Poisson's ratio, which is 0.38, by the way, to calculate exactly how much that cable will stretch and thin out under that crazy amount of tension, just to guarantee it won't thin out too much and snap while you're standing right next to it.
Section 3. Pushing past the breaking point. Entering the plastic zone.
So what happens when the load is simply too heavy and a material is pushed way beyond its limits? We really need to contrast two different realities here. Like we talked about, elastic deformation is temporary. It bounces back. But if you apply enough stress, you hit a threshold where the deformation becomes plastic.
And I should clarify, in engineering physics, the word plastic literally just means permanent. Once plastic deformation occurs, the material is never going back to its original shape. It's like pulling a metal slinky just a little too hard. It's ruined forever.
Let's look at the micromechanics of this permanent change. Unlike the elastic phase, where bonds just sort of stretch comfortably, here, massive numbers of atoms are violently sliding past one another. The original atomic bonds are literally breaking apart, atomic planes are shearing, and atoms are being forced to make completely new bonds with completely new neighbors. Because of this massive internal structural shift, even when you remove the stress, the atoms just can't find their way back home. The change is irreversible.
Now, because we really don't want our bridges, buildings, or airplanes to permanently warp while we're inside them, engineers rely on a crucial safety metric called yield strength. Yield strength is, in essence, a material's maximum tolerance before it undergoes permanent plastic deformation. Keep the stress below the yield strength, and the material will bounce right back. Go over it, you've permanently bent it out of shape.
Finding the exact microscopic onset of this plastic deformation is, as you can imagine, incredibly tricky. It's not always obvious. So the industry uses a really clever standardized trick called the 0.002 offset method. Engineers basically draw a line parallel to the material's elastic region, but shift it over by a tiny strain of 0.2%. The exact spot where that parallel line intersects the stress-strain curve, that becomes our definitive official yield strength.
Section 4. Measuring toughness and hardness, the final verdict before failure.
How do we actually evaluate materials against their extreme limits right before they fail completely? Well, in material science, the word toughness isn't just a generic adjective. It is a very specific, measurable property. It dictates a material's resistance to fracturing when a crack is already present. We literally calculate toughness by measuring the entire shaded area underneath a stress-strain curve. A brittle material, like say a ceramic coffee mug, has a steep, narrow curve. It's strong, but it snaps almost instantly. A ductile material, like a structural metal, has a wide, sweeping curve. It absorbs massive amounts of energy before it finally gives up and fractures.
So the crucial point here is this. For a material to genuinely be considered tough, it absolutely must display two things at the exact same time. It needs high strength, meaning it can carry a heavy load, and large ductility, meaning it can stretch and deform significantly without snapping. You literally need both of those traits to survive the harshest conditions out there.
Now, toughness is mostly about stopping internal cracks from spreading and causing a catastrophic failure. But what about the outside? That is where hardness comes in. Hardness is all about a material's resistance to localized surface damage. For metals, engineers use indentation tests, like the Brittleness test, where they basically just force a super hard steel ball into the surface and measure how deep the dent is. Simple, right? For brittle materials that would just shatter if you hit them with a steel ball, hardness is defined purely by scratch resistance, and that's measured using the classic Mohs scale. And that brings us to the end of today's explainer on mechanical properties. We've journeyed all the way from microscopic atomic bonds stretching and snapping back into place to calculating the exact mathematical moment a steel winch cable will permanently deform. It really changes the way you look at the built environment around us, doesn't it? So I'll leave you with this final thought. The next time you're walking past a towering skyscraper or driving over a massive suspension bridge, ask yourself what invisible forces of tension and compression are quietly shaping that structure right at this very moment, and just how tough are the materials keeping it standing. Keep questioning the world around you, keep learning, and we will catch you in the next explainer.